everyone, and welcome to today's discovery session. These sessions are meant to support students, businesses, and other organizations with an understanding of how to use data and artificial intelligence. Before we get started, I would like to begin by acknowledging that DeepSense works out of Mi'kmaqi, the ancestral and unceded territory of Mi'kmaq people. This territory is covered by the treaties of peace and friendship. I would like to acknowledge the indigenous peoples whose traditional lands we are on today and ask that everyone take a moment to consider the territory in which they're situated as well as their own personal responsibility in the processes of reconciliation. My name is Agastya, and I'm the Junior Communications Specialist at DeepSense. For those of you who do not know, DeepSense is an organization based out of the Faculty of Computer Science at Dalhousie University, whose mission is to help grow the marine economy with artificial intelligence. By leveraging a unique project structure, DeepSense delivers high impact machine learning and AI applied research projects for the ocean industry. These research projects expose students to real world applications of advanced technology, preparing them for success in the rapidly growing blue economy, while also enabling marine focused businesses with advanced AI capabilities. If you're like a student and you're looking to expand your skills, work on real projects, and also like gain valuable industry experience, be sure to submit your information to our student pool, which I will drop the link to in the chat box shortly. Now, for today's discovery session, this session will provide a broad overview of reinforcement learning, which is a branch of AI focused on training agents to make optimal decisions through interaction with their environment. We'll explore a couple of key concepts, real-world applications, and why reinforcement learning matters for the industry and research. Bryce, who is our speaker, will also discuss how reinforcement learning is starting to take shape within DeepSense projects and also where it could contribute to the future of ocean AI. Our session today is led by Bryce MacInnis. Bryce is a data and AI algorithms lead at DeepSense, based out of the Pier, and a researcher at Dalhousie University. At DeepSense, he supports applied projects by mentoring interns, guiding model development, and helping shape solutions to real-world challenges. His research spans applications in robotics, network optimization, and also a lot of like emerging marine sectors. If you have questions throughout the presentation, you can raise your hand or you can drop it in the chat box and we can take them either during our small break whenever Bryce can answer them, or we will answer them at the end. But feel free to drop them in the chat at any point during the presentation. All right, that's enough for me, and now let's hear from Bryce.
Cool. Thank you, Augustia. I'll share my screen here. And like you said, Augustia, it's a small group today. So if there's any questions, feel free to raise your hand and I'll do my best to monitor the chat so I can answer those questions. Can everyone see the keynote?
Yep.
Okay, I'm just going to try to maximize this. Still good?
Yeah, I can see it.
Okay, perfect. So what is reinforcement learning? Probably best seen and not told. This is a robot named Cassie. It's a delivery robot that's being invented in Berkeley in California. And they call it a delivery ostrich because it's a bipedal walker and it looks and it resembles like an ostrich. And it most likely learned how to walk through reinforcement learning because that's the most common way that you'll train robotics and nowadays in machine learning. So let's go over some vocabulary first so we can all be on the same page about what words we're using. An agent is something that you're trying to learn a policy for. So a policy is how to make decisions or how to control something in an environment. So for example, if you want to learn how to, say, use a ping pong ball, the agent is the arm that controls the ping pong racket. The policy is deciding when to use that racket and how to use that racket as how to control it. And the environment is the ping pong table and likely the game. For example, a trajectory is if you're trying to land a lunar lander, the trajectory is a path that you're going to take and decisions that you're going to make over your entire interaction with the environment. A state is any part of a trajectory. So that is the observations from the environment, like external variables, like how far in the air you are, the current speed you're going, and yeah. Action is any action that you can take within the environment, and that affects your next state. But mainly an action could be, for example, if you're trying to learn how to play a game, an action could be as simple as pressing a button on a controller, moving a joystick, or it could be more involved, like, uh, for example, translate the leg by 15 degrees. So what's machine learning? We'll start with the basics. Machine learning is all based on one idea that computers should be able to solve problems without being explicitly programmed how to do it. So it's moving away from the algorithms of, say, the 80s and the 90s, or the expert systems that have experts telling the program exactly how to solve a problem. Machine learning is this idea that computers should be able to figure out problems by themselves in the same way that humans learn without having to be programmed to do so. Reinforcement learning is just a specialization of that, but it's the idea that computers should be able to learn how to play games, how to make decisions, how to strategize, and how to control things. When I say control things, I typically mean robots, but it could be things like wind turbines or power plants, anything that has a decision-making process. So how did reinforcement learning start? This is Richard Sutton on the left, sorry. And he's a researcher at University of Alberta. He's also a research chair at Google DeepMind, and he was responsible for starting the first Google DeepMind branch in Alberta, in Edmonton. He is a computer scientist, and he's been working on reinforcement learning. Really, he made the field of reinforcement learning since the 1980s when he was working on it as a professor. And to his right, that is Andrew Bardo. And Andrew Bardo is a cognitive scientist working in the US. And between the two of them, they merged psychology together and computer science together to come up with the field of reinforcement learning. So how is it different than any other kind of machine learning? Typically in supervised learning, you have an error function that you use to train the neural network that says basically what you want and how far away you are from it. Then in unsupervised learning, if you're familiar, there is no error function, or there is no ground truth to tell you how close you are. Uh, Reinforcement learning is one step further than unsupervised learning, where now you have this feedback loop where the agent interacts with the environment, and the environment affects how the agent interacts. So this feedback loop leads to some new issues that you don't see in things like unsupervised learning, because there's this element of having to explore your environment. What you do affects the environment, and it affects the search space. So if you're not familiar with reinforcement learning, you might be familiar with some of the successes. This is AlphaGo. So Go is a very complicated game, a little bit more advanced in terms of search space than, say, chess. AlphaGo, I think in 2016, maybe a little bit later, was the first time that a computer was able to beat a human at playing AlphaGo, or at playing the game Go. Similarly, AlphaFold is for discovering new proteins and how they fold, and it's being used to accelerate drug discovery for things like maybe like vaccines or medicines. But it just recently won a Nobel Prize from Google's research and Geoffrey Hinton at University of Toronto for all the contributions that machine learning makes to physics, and in this case, chemistry. So every reinforcement learning problem can be modeled by a Markov decision process. And I'll give you the mathematical definition. It's a set of four tuples, state, action, and reward, and the transition matrix. But really, to simplify it, everything is broken down. Every decision-making problem is broken down into a flow chart. So S0, S1, S2, these are possible states that you might be in. For example, if you're talking about going to class or being a university student, state 0 might be studying, state 1 might be in transit, say taking a bus, and state 2 might be celebrating after work at drinks or partying or enjoying life. So Markov decision process tells you how likely you are to take an action. So for example, if you want to go from studying to going to go get drinks, and you first have to take action 0 and move to state 1, which is the transit. And then from there, move to state 2, which is the bar. So edge in that graph is a transition with a certain amount of probability. And for each edge, for each action that you take, for each state action pair, there's a reward associated with it. So as you can imagine, maybe studying is granted a high reward because you're moving ahead in your academics, whereas going to drinking, there might be a suboptimal award where you have a lot of fun, but also maybe you have to recover for the next day. And then finally, the transit, which might actually have a penalty associated with it because no one likes being in transit. So the goal of reinforcement learning is to solve a problem by maximizing the cumulative reward by interacting with the environment. So starting with a toy example, maybe best understand it, is the goal here is for the agent to move from this cell on the far left of the grid to all the way to the star pattern in the top right corner. When the agent reaches that star pattern, it's given 100 reward. So a positive reward for reaching that star pattern. But when you hit a wall, there's a penalty, aka getting hurt. So the way that value estimation works is that you do means end analysis, which is a concept that came all the way back in Aristotle's day, which is basically saying, look where you want to be, that's a goal state, and work your way backwards from it. So if the goal state is 100 reward, then all of the rewards in the adjacent areas are closer and closer. So it's closer and closer to 100. And it should cause some sort of bucket brigade. So that's rewards from future states are passing backwards in time. So there's a intermediate or a intermediary reward being passed to the agent at the starting state. So for example, one way to formalize this idea of passing rewards back in time so you can start working your way from backwards to the next move you want to make immediately is something called a temporal difference method, or in other words, how to bootstrap a value function. So what a value function does is it tells you how good a state is to be in. So for example, the state above and below the person right now is suboptimal to the state that's directly to the right and one that advances you to the end goal. One of the core principles of designing a value function is that value function should be a consistent value function. And that's even more important than solving the task. Now, for example, if I wanted to know how good it was to be in the cell right next to the agent in this grid, if at one turn I tell you it's really, really good to be in that position, and the next turn I say, actually, maybe not, maybe I'm not sure about that. And then I keep flip-flopping back and forth. So what you see on the left is a noisy grid of a reward signal or a value function saying how good that state is. What's really bad is to have an inconsistent result. So it's total lack of confidence or total high entropy. You can't really say whether that state is good or not. The ideal thing for a value function is to have a smooth curve. So you can say that cell adjacent to the agent here is pretty good. And you're pretty good each turn. So that way the agent has consistent reward signal to follow in solving this problem. So how do you learn a value function? It comes down to these equations here, the Bellman equations. So there's mathematical formulations for each one. They look complicated, but they aren't that complicated. So the value of a state, that is how good it is to be in that state, is the reward you get for being in that state. So for example, 0 in this case, with adjacent right to the right next one, because there's no reward for being in a neutral spot. You only get a reward or penalty for hitting a wall or for reaching the star. So in that case, the reward for that state is 0. But this next term is a weighted average of all possible future states that you can be at from that state. So it looks at an average of all the other states in this grid, and it tells you how good it is to be in those states. What happens is you train this iteratively. So you work your way backwards, each updating a state based on how good it is or how close it is to neighboring states that are also good. But what that winds up doing is moving that star reward backwards in time towards the agent. And that's where the bucket brigade metaphor begins. Similarly, this value function can be extended to what they call a Q function. And that tells you how good is it to take an action at this state. So for example, we already know a value function that tells you how good it is to be in state free 1 or free 2. But what you want to know is, should I go right? Should I go up? Should I go down? Or should I go left? So using the Q function, you can actually get an answer to that. So it'll tell you how good each action is. And if you want to maximize the reward, then you should choose one with the highest Q value. The Q function and the value function are closely derived to each other. So you can totally derive the Q function just from the value function with a little bit of algebraic manipulation. But the important thing is you have a function that tells you how good a state is, and you also have a function that tells you how good an action is if you're in that state. And ideally, you want that value function to be consistent over time. But it gets more complicated than that. So in reinforcement learning, there's always a question of exploration or exploitation. And the idea is, if you know that something's good, then you want to be able to keep doing the same thing over and over. Like for example, if you know that one slot machine at a casino is really giving you like lots of money back, you want to keep using it over and over and over and over. But what actually if there's another slot machine that maybe your lucky break is going to be there? There's going to be like a jackpot and you're going to win. In such a case, there's a question of should the agent keep exploiting what it's already giving a good reward, or maybe there's something better. This gets even more complicated in things that are called non-stationary environments. So for example, things might change, and what used to be good in the past doesn't mean it'll be good in the future. So the whole point of the exploration versus exploitation dilemma is, when should I move on to trying the next thing? Or did the previous thing change? So if you want the highest reward possible when solving a problem, you should exploit the most optimal strategy. But when that optimal strategy changes, or the thing that you thought was optimal is actually suboptimal, then you actually maybe need to explore more options. So what they do typically in reinforcement learning is they have an algorithm called E to greedy or epsilon greedy, which says 15% of the time, or epsilon percent of the time, choose a random action. That encourages exploration. And for the rest of the time, choose what you think is the best action. So sometimes you choose something randomly, other times you'll choose the best thing. And that encourages a balance between exploration and exploitation. But moving on to the applied aspects, deep Q learning was the first time that reinforcement learning really became popular again from back in the 1980s and 1990s when Richard Sutton and Andrew Barta were working on it. And what was motivated is that in 2016, AlexNet was released where they were using computer vision for classifying images. Like, for example, this is a dog, this is a cat. Well, they were wondering at Google DeepMind whether or not you do the same thing. You can use the same techniques to solve problems like play Atari games or play chess. So what they did is they strapped a convolutional neural network in the same way that you would use a CNN to classify whether something's a cat or a dog, and they attached it on to a multi-layer perceptron or neural network. So they have a convolutional neural network at the front, then you have a neural network, and what you're trying to do is you're trying to minimize these equations here so you get a consistent predictor of how good something is. Once you have a predictor of how good something is, you simply just choose the best action for the state that you're in. And what they found is, yes, actually a neural network with a CNN using temporal difference error can actually solve most Atari games. So this accelerated a lot of research back into reinforcement learning, and it's where it is today because of that. I'd like to bring up maybe some alternative paradigms to reinforcement learning other than, say, a neural network. And that's maybe genetic programming, where you start with a population of candidate solutions. So for example, equations that you might think solve the problem. Then you choose which population is doing the best. So there's some metric of fitness. So what was the reward that the individual got on the task? And if it got a high reward, then you want to keep that individual. Now, similar to natural selection in nature, you have this idea of variation. So you take the best programs that you have, or the best solutions that you have, you vary them a little bit, and you keep this process going and going until you get slightly better population across maybe 1,000 generations, and you're left with a population that's actually highly fit to solving the problem. A further advancement of genetic programming for solving more complex problems is to evolve a network of programs. This is an extension of genetic programming, And it's actually similar to how the brain is developed. So for example, the brain has the medulla oblongata for learning how to control, like the lizard brain, as they say, where you have like basic functions like learning to, or knowing how to breathe, knowing how to regulate your temperature. But then there's things like the prefrontal cortex, which is reasoning. So there's specializations of the brain. This is taking the same kind of idea where you start with a root node in the middle, that's a black dot, and then you have a team of programs that are all competing to suggest the action. So what happens is the black dot chooses the program that's most confident in itself, and then that program gets to suggest either an action or it gets to point to another program that it thinks knows the action. So for example, this black dot will ask the 6 points around it, which program should I trust here? And the one that's most confident is going to emerge, trust me, and I'll refer you to the next either person that can give you an answer or the next action that you should take. So basically, it's the same as genetic programming where you're evolving problems or evolving programs to solve a problem. But in this case, you actually have networks of programs solving a problem. What they found is that TPG, or tangled program graphs, are competitive with deep key learning at things like the Atari environment, things like controlling robots, and basically anything else that reinforcement learning can do. There's also other ways of training a neural network. So for example, neuroevolution. So typically when you think training a neural network, you think of gradient descent, where you're trying to optimize weights and basically you take the error signal and you try to minimize that error signal and update the weights according to that gradient or according to that derivative. But really, there's other ways of doing it. One such way is another evolutionary algorithm called CMA, covariance matrix augmentation. So basically, it spreads the search across 1,000 individuals and it moves towards the area where there's most covariance. And then eventually it hones in. So for example, this graph, it starts in a suboptimal point, which is yellow, and moves to hotter temperatures, aka the white, where the hotter temperatures are considered as more rewarding or associated with a higher reward. So you see that all these blue dots are potential solutions in the population. And what they do is over time, they hone in on the most optimal point within that search space. One good thing about CMA ES is that it's less likely to get stuck in local optima. So one thing about neural networks is that they often find suboptimal solutions. CMA ES is a natural defense against that because it has a population of solutions. Rather than trying to move one solution around and possibly getting stuck in the local valleys in the fitness landscape or local minimums. Then what CMA does is it has 1,000 populations, and having a diversity or variation of individual programs within the search or within the search process makes it less likely to get stuck in local optima. The other thing that is an inherent assumption of neural networks is that they assume differentiability, so that reward signal has information on how to move from one step to the next, essentially. But with many problems of sparse rewards, that is, you don't get a reward signal telling you how well you're doing in between steps. Well, instead, all you say is, yes, you did the task. No, you didn't do the task. So you get +1 reward if you win, or 0 reward if you don't win. So you don't get lots of intermediate information saying, oh yeah, you're getting better, you're getting hotter, you're getting colder. You only get that reward at the end. So that's one reason why CMA might be preferred in some domains where you have sparse rewards. I'm gonna do a quick check back for questions. Nope, no questions. Okay. Okay, so policy gradients. So what we've described up to now is suggesting a discrete action. So you have a bunch of actions from a list and you're trying to choose which action is the best action to choose. So for example, actions might be buttons on an Atari controller and you're wondering what button combination should I push? But it's pretty easy to choose which action because you just exhaustively look at each action in the list and say which one's gonna get me the highest reward. Yeah, same thing on that. But in the case of continuous environments where it's not a list of actions anymore, it's saying, how much do I move this leg by? How much should I control my speed by? How should I do this? Or what strategy or what trajectory should I plan? Now you have this problem where you have to suggest an action. And the action is an infinite search space. So you can't go through each one because it's an infinite amount of different
Hi.
actions.
Sorry, Bryce,
Sorry.
sorry for like stopping you in the middle. I
Yeah.
don't see your slides. Could you like share your screen again?
Oh, sorry about that.
No, of course. Thank you.
Must have got disrupted when I.
Yeah, that happens a lot.
Yeah. Okay, I'll go back.
Yeah, we can see the screen now.
Okay, perfect.
Perfect.
Continue. Yes. Okay. So, for example, if we go back to this TPG representation, F, A, B, S, R are all controllers that you can push on the Atari controller. Whereas, for example, these policy gradient methods where you have to learn how to walk or have to learn how to control a robot, or you have to learn how to control like a bipedal walker or an ostrich, for example, you don't get the liberty of saying, oh, press the A button or press the B button. There's no finite list of actions that you can choose from. In this case, you have an infinite space of actions that you can choose from. For example, move your leg 0.5 degrees, move your leg 25 degrees, move your leg 30 degrees, do this speed. So in this case, now you have to have something that tells you how good an action is for every state that you're in. But you also need to have an actor network to actually suggest an action to do. So for example, I'll just say it this way. You have two networks. One neural network has to tell you how good is the action going to be if you take it. And the second network is going to tell you what action should you take in the first place. So these two networks work side by side. One's called an actor network, which tells you what to do, and a critic network tells you how good that action is. So two of the most famous reinforcement learning algorithms are TD3 and soft actor critic. These are both policy gradient methods, and you'll see these most often. So one of the objectives I have in talking about this discovery session is not to give you a complete understanding of reinforcement learning, because that's not possible within an hour, but to give you a lay of the land. So some of these terms that you might see online, if you're interested in reinforcement learning, like TD3 and soft actor critic, what's a policy gradient, what's a continuous environment. Hopefully this kind of precedes you with some background so you can better understand things that you read. On that, off policy versus on policy. So what's the difference in reinforcement learning? And basically off policy is all about data efficiency. So when you're learning how to control a robot like this, you get a reward after taking action. So for example, I say, move my left leg by 15 degrees. And you say, good job, that was what you're supposed to do. Here's a +1 reward. But reinforcement learning algorithms until now just discard that information. And discarding that information means you have to interact with the simulator a lot. But the simulator is a CPU intensive process. It's a physics simulator, so it's quite expensive for your computer to run. And really, it's a terrific waste of data to get rid of all that information just because you're not using it anymore. So the idea of off policy is you're gonna save as much data as you can so you can learn as efficiently from the data you've stored as possible. So on policy throws the data away. Off policy tries to conserve the data by storing it in a buffer. One of the things about a neural network is because they do work in the iterative method, gradient descent, is that they require a lot of data. So off policy is basically necessary for any difficult reinforcement learning task. Then there's cases of model safety. So let's think about a use case like a self-driving car. Typically, like if you're interacting with an environment like this, your robot falls down in a simulator, no real issue. But say you actually want to bring something onto a road. How do you know if your model is safe or not? And if you do choose the wrong action, it can be disastrous. Like for example, there's a pedestrian crossing. Do you want to hit the gas? Well, your algorithm says so, but if you do hit the gas while a pedestrian's crossing, it's going to be a disaster. So it's one of these issues that you have to solve. And one way to solve that issue is through an algorithm called Trust Region Policy Optimization, or TRPO. And basically, there's a lot of math behind it in terms of what action to choose, But the idea of it, the underlying intuition, is don't do things that you aren't confident about. So, for example, if there's a pedestrian crossing and you're kind of sure maybe I should press the gas, but you also don't know if you should stop, then definitely don't do that. You need to have 99% confidence. Like, I should 100% push the gas. You need to be totally in control. So that's the idea of using TRPO. Behind the scenes, TRPO is hard to train. It's quite mathematically rigorous. So there's a simpler algorithm called PPO. And I'd say probably the most famous reinforcement learning algorithm is PPO. Really, it's the same as any other reinforcement learning algorithm where you're trying to maximize reward by interacting with the environment. But the focus of PPO is making sure you don't do the wrong things that could cause problems. So it's not just self-driving cars. If you're training an expensive robot, you don't want your robot to fall down and break something because then you're going to be out lots of money. So PPO is one of those algorithms that are trained with model safety directly in mind. So you don't want to do actions that you aren't sure of. So because we just covered a bunch of different algorithms, we'll go slowly through each one. Deep Q learning networks are the earliest attempt to use computer vision. They were inspired by AlexNet in 2016. So when machine learning was starting to really take off. And really what it's trying to do is take that same architecture it uses for computer vision and apply it to solving problems with high dimensional environments. So high dimensional environments are like you're just given a screen from an Atari game and it's a say 300 by 90 pixel resolution. So each pixel is given as input and you're trying to learn how to solve the problem. You're trying to learn how to play the game and get the highest score in the game. Sorry, it's a mouthful, but DQN is basically the first attempt at solving games with neural networks. Genetic programming and TPG are an alternative paradigm to neural networks that are arguably just as good. And one of the reasons that people like genetic programming over TPG is that they're interpretable. Like, for example, they go all the way back here. This is a syntax tree. So it's times plus minus yx. So you can kind of get if you look into the black box here, you can kind of see this is the calculation it's doing to solve the problem. Whereas, for example, if you look at a neural network, sorry, it's probably in DQN, there's so many different edges and connections that you can't really understand what's happening. Whereas if GP, it's a lot simpler. In fact, with GP, you start with a simple solution and you complexify as needed. Whereas for neural networks, you start with a complex architecture and you turn off the neuron edges if they're not useful. Neuroevolution is one other strategy. So it's the CMA that we talked about, where you have a neural network, but instead of using gradient descent, you're using some sort of other optimization algorithm, in this case, CMA. And that could be useful for sparse reward environments or environments that don't have a differentiable reward signal. TD-free and soft vector critic are off-policy methods, so methods that are trying to save data by storing it in a buffer. And these methods are currently considered state-of-the-art in reinforcement learning. They've been around since 2018, and they're basically used for any reinforcement learning problem that you see in practice today. On the other hand, you might still see PPO for some things where model safety is really important. So making the wrong action or making the wrong choice in the wrong time can lead to bad consequences. You might tend to prefer PPO over TD-free or soft vector critic. So challenges. These are the challenges that reinforcement learning faces today. You want interpretable solutions, and the neural network in deep reinforcement learning all the way back here is a black box. So you don't really know why you took that action in that state. And if you're trying to trust something like a self-driving car, you want to know why it did something. So you want to have some sort of explanation of why it did something. So one of the challenges that you see today are trying to get interpretable solutions. So for example, explainable results. Like I chose this action because of these variables at this time. And typically you'll see methods like genetic programming or TPG being used as interpretable alternatives to deep reinforcement learning. Still today, there's issues of sample efficiency. So for example, you have data from a really expensive simulator. Even using off policies, still have to interact with the simulator a bunch. So trying to be more efficient with the data that you use. One method of solving this problem is something called offline reinforcement learning, where instead of interacting with the environment at all, you have a fixed data set of interactions that you recorded. So for example, you want to learn how to use a crane to solve, or you want to learn how to use like a tractor to dig a hole. Well, instead of trying to model one in a simulator, interacting with that simulator, maybe instead you can attach sensors to the tractor and learn from a data set of how those sensors worked. So you can learn how to use the tractor by watching by a human operating the tractor and replicate that through reinforcement learning. Model safety, we talked about with PPO and TRPO, but increasingly as reinforcement learning gets applied in the industry, you want to have some guarantees around safety, and enforce or showing that you have actual guarantees is an increasing area of research. And right now, the reason why you don't see reinforcement learning as often applied to say supervised learning or unsupervised learning is that it's difficult to design a reward function. So oftentimes there's something called an alignment gap. So where you reward something for some action and you assume that's the right way to do it, but really the algorithm finds some tricky, trivial solution that gets around or cheats essentially. So I'll give an example of this. You're trying to land a rocket ship, and the closer you can get to that rocket ship landing on the moon, the better. When you crash a rocket ship on the moon, you get punished, but the closer you get to the moon, the better reward that you get. So for example, a reward function, you might think you reward it for getting really close to the moon, and you penalize it for any damage that it takes on the way down. But really, there's a solution that I've seen personally happen in practice with neural networks and deep reinforcement learning in general, or reinforcement learning in general, even more so than deep reinforcement learning, is that the best solution in this case is just to hover against the ground. So don't land the rope or don't land the rocket at all. Just hover. So you're close to the moon, so you get a high reward for being close to the moon, but you never crash because you never try to land. So there's alignment gaps where what you think is going to work as a reward function might lead to some less than desirable behavior. Also, just in general, reinforcement learning solves complicated problems in complex and dynamic environments. And being able to create like a simulator or a model of that environment is really difficult. So the last final problem is when you have that sparse reward, like I mentioned, where you don't get any feedback. Like, for example, when you're with a driving instructor, typically you'll get feedback like, oh, you forgot to do a lane change. Oh, you forgot or going too fast. Oh, you weren't smooth on the brakes. In this case, a sparse reward is not getting intermediate feedback like that. A sparse reward is you passed your test, you failed your test. Thumb up or thumb down. So because you don't have a reward signal on that, it's really difficult to use gradient descent to solve a problem. Now to talk about some hot areas of research, model-based reinforcement learning. So that's when you're trying to actually learn your environment and store it in memory. So right now, reinforcement learning agents don't have any concept of memory. So if you want like conceptualize this, for example, if you have a Roomba or a smart vacuum that goes around your house, building a model is learning what your house looks like. That way, instead of just bumping into walls, you actually have this mental map of what your house looks like. I mentioned offline reinforcement learning earlier, but for example, you have some sort of expert data set where you have a human that demonstrated how to solve a problem and you've collected data on how to solve that problem, then reinforcement learning should be able to learn from that data directly without interacting with the environment any further. That's quite a hot area of research. Another one is multi-agent reinforcement learning. So for example, in all the problems that we've seen so far, it's always one agent. So learning how for one agent to walk or another agent to walk. But in the case of say like a soccer team, these agents have to coordinate with each other. So you have to have a striker, you need to have a defenseman, you need to have people pass the ball. So learning how to coordinate and train multiple things simultaneously and in parallel is multi-agent reinforcement learning, and it's quite an active area of development. Similar to that is multitask reinforcement learning. So if something is good at playing soccer, but can you train it to also be good at basketball? Can you train it to be good at hockey? So instead of just being good at one task domain, can you take your pre-trained model and tune it or fine tune it to another environment? That's multitask reinforcement learning. Interpretable reinforcement learning, like genetic programming, might be a solution for, is again having explainability behind why you made those decisions. So why did you choose this action? Was it the best action to choose? What were the variables that made you decide to choose that action over another action? That might be also useful, like if you have a problem that we don't know how to solve, if you throw a reinforcement learning agent on it, can we learn how to solve a problem just by directly watching the agent learn uh, through gradient descent? And finally, multi-objective reinforcement learning is something that you see pop up quite often. And that's when you have two competing objectives. So for example, what would it be? For example, you're trying to have a car that goes really fast. You're trying to learn like a policy that learns how to race cars. Well, in which case, you really want to have the fastest driver possible. But then you also have this other objective where you don't want to crash your car and explode. So you have safety and you have speed. And both of these are competitive. So if you have a car that goes really, really fast, but there's no safety involved, that's not a really good action or not really good policy to learn. But if you have a car that goes really, really slow, but it's really, really safe, like it doesn't move out of the parking lot, then that's not a really good driving policy either. So you need to have some sort of algorithm that balances both objectives, especially when those objectives are in tension. So if we talk about now how reinforcement learning connects to the ocean industry or the ocean sector, I can point to a couple case studies. Uh, for example, autonomous underwater vehicles, a bit like the Roomba example I just mentioned, where you learn an environment. So you learn a model of the environment. So for example, these are areas of high currents. These are outcrops that you want to avoid bumping into. And you want to map the ocean floor for either bathymetry or you want to map the ocean floor for measuring catch. In this case, you can reward the agent for how much of the area it covered, so percentage of area covered. And then you can penalize it for going in dangerous actions, like being too close to the shore, brushing up against something that you don't want to brush up against, or going to a whirlpool where you spend excess of gas. So really the goal here is much like a Roomba would. You're trying to learn your environment and you're trying to avoid bumping into things or doing anything that's undesirable. Another example for fishing with reinforcement learning is a trawling net. So for example, what I know about fish is that they swim at different levels. So you have some fish that swim at the top of the water column, while you have other fish that are mid-level swimmers, and you have other fish that are bottom feeders, so they're always at the bottom. So one thing that you want to do is you want to learn how to control this trawling net, because really what you want to do is you want to catch the fish that you're looking for, and you don't want to catch the fish that you aren't looking for. That's bycatch, and that's not desirable. So what you have to learn to do is you have to learn how to control these ropes. So how much slack do I give the rope to control the one net to be in the optimal location? So how do you learn how to do that policy? Well, you reward it for catching the fish that you want to catch, and you penalize it for catching a fish that you don't want to catch. And over time, based on the conditions of its sensors and how long a rope it's known to be, it'll learn over time to optimize itself to only catch what you want to catch and to minimize catching what you don't want to catch. So that's one way that reinforcement learning can be used to improve trawling systems. And then it can also be used in wave and tidal energy. So underwater currents are lots of power, so they're great for tidal power and tidal energy plants, but they're also dynamic and complicated. And predicting water currents is very complicated even still, even in the rise of machine learning. So you have this trade-off here, where you want to generate power by having a lot of resistance against the waves, but if you have too much power, then the waves are going to damage your turbine. On the other hand, if you don't have enough power generated by the waves, then you're not going to generate the electricity that you need. So you can adjust this balance by rotating the turbine blades. So if they're in the correct orientation, then the waves will push it with an ideal amount of pressure. So you can learn how to rotate these waves or rotate these blades. So you have the optimal amount of pressure on it so you generate the most electricity while also avoiding possible risks like too much pressure and damaging your turbine. It's very expensive to repair. So in this case, the reward function is really simple. It's some quantification of how much damage there is or how much average pressure there is on the blade. So you get a penalty for having too much pressure on the blade, and you get a reward for the amount of kilowatts per hour that you generate. So over time, by learning through, say, a temporal difference algorithm or a deep reinforcement learning in general, then what you'll have is you'll have a policy that learns how to control the blades to be both safe and to generate lots of power. And finally, the last case study that we're talking about is illegal fishing monitoring. So in this case, we have patrol ships that are looking for poachers trying to catch whales or some protected species that you're not allowed to fish for. And in this case, you have a reward for detecting suspicious activity. So what you have is you have patrol ships going around this ocean area, and you're looking for illegal fishing. And what the patrol ships have to do is they have to decide the best routes to go to detect these illegal fishers. But you don't want to cause too much human labor time, so you don't want to go an inefficient route that takes a long time and doesn't actually detect any fishing. And there's other costs associated with that, like the amount of fuel that you have, or basically you want to be as efficient in the routes that you plan. So you want to have these golden routes so you can catch lots of legal fishers. And then in this case, you can use reinforcement learning to do that. So you plan a route and you reward the agent for choosing a good route if he detects suspicious activity on that route. But then you penalize it for how big of a trajectory or how big of a route it suggests. So over time, when you train this, what you expect to see is you expect to see shorter routes catching more illegal fishing. And the end goal of that would be reducing the amount of human labor it costs to patrol ships and reducing the amount of fuel used. And by by reducing the amount of fuel, also improving carbon emissions. So if you're interested in getting started with reinforcement learning, one of the best areas is gymnasium environments. It's released by OpenAI to encourage reinforcement learning development. It's no longer being maintained by OpenAI. It's now a nonprofit from a foundation. But what they do is they use easy to use APIs so you can get started interacting with these environments. So in this case, this is a lunar lander trying to land on the moon. And it gives you an API so you can play with the simulator and just focus on the reinforcement learning algorithm itself. What's also really great about these gymnasium environments is you often see them as benchmarks in reinforcement learning papers. So if you're looking to publish a reinforcement learning paper, you want to have some sort of standardized metric of how well your reinforcement learning algorithm does. And these gymnasium environments are a good place to start and are widely used by other researchers. Similarly, these Majoko environments are more complicated than the gymnasium environments. The gymnasium environments tend to be discrete actions. So what buttons in the controller do you use, or what engine do you fire in this case of the lunar lander? The Majoko environments are locomotion tasks. So again, continuous environments. How much do you move each joint by? How much each limb by in order to have like the fastest walk that you can? So in this case, the agent is rewarded for the amount of distance that it travels. So if it can sprint really fast in a fixed amount of time, then it's going to get a high reward. But if it's unstable and it falls down like this one, then in that case, it's going to get a negative reward or little reward. And if you want to, we only covered a little bit in this survey of reinforcement learning, so hopefully enough to get you a gist of what's happening in the field. But if you want to get started with actually understanding it at a deeper level, there's an OpenAI spinning up guide that teaches you key concepts in reinforcement learning, the different kinds of algorithms like PPO, TD-free, soft actor critic, many more, and things that you might want to work on, like projects or things that OpenAI are interested in that maybe can lead you to a job at OpenAI. That's good for getting started in terms of actually what do I do now. But if you want to understand the deeper theory, there's no better place than the Bible of Reinforcement Learning, Reinforcement Learning and Introduction by Richard Sutton and Andrew Bardo, the inventors of the field. And I think it's particularly cool that Richard Sutton is still in Alberta, so a Canadian researcher, and he's been here for the last 20 years. Okay, I'll stop the questions.
That was amazing. Thank you so much, Bryce. I also like especially like the last part where, you tell the students if they're like interested in learning about like reinforcement learning, where they can like go and build on those foundational skills. So I think those are like really good resources. And if you have like any questions, you can like drop them in the chat, or even raise your hand. I did have a question. Sorry. Yeah, so like, from an industry perspective, since you're in the industry, what are like some practical opportunities where reinforcement learning could, create immediate impact in the marine technology?
Yeah, those case studies I did kind of cover some suggestions for where you can start out. So, example, anything where you have to control something. So, like the best example that I've seen in practice is at what level do you control a trawling net? So, you want to reduce the amount of bycatch. There's many problems that can be solved by reinforcement learning. My suggestion is to see greater adoption of reinforcement learning in the field, is to be familiar with reinforcement learning itself and see where it can be applied to solve problems. Because
Hmm.
when I work with people at DeepSense, they're often not familiar with reinforcement learning, so they can't view the problem as a reinforcement learning problem to solve. So if you
Yeah,
have these skills, I'm positive you'll see lots of reinforcement learning areas, and we'd love to have you at DeepSense. So here's a plug to join our student pool and get solving reinforcement learning problems with me.
yeah, that's fair. And I also like wanted to know like how do you see like reinforcement learning being applied in the ocean sector in the near future, and like what are some challenges that you think that need to be like tackled before we even get to that point?
Yeah, so some of the issues or challenges that are blocking reinforcement learning are the complexity of modeling environments. So I think the biggest one would be offline reinforcement learning, which is where my particular area of research is. Offline reinforcement learning means that you don't have to model complex environments anymore. You learn from real data. So with that taking off more and more, we have a project with DeepSense where we do offline reinforcement learning coming up. I can see much more industry application. In terms of what problems can reinforcement learning solve, I would say underwater vehicles are a big one. Uh, Learning how to use power efficiently. So reinforcement learning powers a lot of power plants. So where that's efficiently using resources in fisheries, efficiently using resources in say wind turbines or hydroelectric dams. There's lots of decision problems to be solved with reinforcement learning there.
Hmm. And we have a question here. So,
Yeah.
what machine learning problem is reinforcement not useful in?
I think personally you can solve many problems with reinforcement learning. I wouldn't
Hmm.
say there's any problem that you can't solve with reinforcement learning, but there's often better tools than reinforcement learning. So in that case, if you have a ground truth, so you have some way of saying this is what it's supposed to be, then it's much easier to reduce as a supervised learning problem.
Hmm.
Really the challenge when you I'd say only use reinforcement learning if you have to use reinforcement learning. If there's a simpler approach, like a supervised approach that you can use, go ahead and use the supervised approach. That's gonna be way faster. But the
Hmm.
challenge of when you have to use reinforcement learning is when you have a feedback loop. That's when the agent interacts with the environment, and how you interact with the environment shapes what you see. So in that dynamic feedback process, that's when you need to use reinforcement learning.
That's a great answer. And like I agree, like it might not be like uh universally applied to like everywhere, but like there's still like other ways where we can, apply reinforcement learning to better like other models. If there's any questions, feel free to like drop them in the chat. And this is just like uh, out of like pure curiosity. So but if you know you had if you could design any dream reinforcement learning project in the ocean sector with like no constraints on limit on budget or time, what do you think it would like look like?
It's a good question. I'm particularly interested in life in the ocean. So I think if you could have a like autonomous robot go around and start mapping all the species that we haven't discovered and learning the different behaviors and trying to understand how those species exist. And I guess if you had like an underwater robot, I could make a little nature documentaries of undiscovered species. I think that'd be a very cool problem.
Yeah, that is actually pretty cool. Like sort of like those ROVs that are like on Mars,
Yep. Yep.
just
Same
like
idea.
exploring. Yeah, that is really cool, honestly. And I don't see any more questions. Um, but yes, thank you so much, Bryce, for like joining us today and like, taking the time out of your extremely busy day to like join us today. I'm sure our participants learned a great deal from your informative talk. And before we end, I wanted to let you all know that I'm going to include the links to our student pool and our social media accounts in this chat. And if you enjoyed today's discovery session, we have recordings of past discovery sessions on our YouTube channel. So smash the like button and you can like access the link in the chat and keep an eye out for more discovery sessions and events from us in the coming months. And you know, before we go, Bryce, do you have any last words before we wrap up?
Yeah, it's a small group today, so feel free to reach out to me directly and we can chat more about reinforcement learning.
Yeah,
I'm
if
always
you
happy to
want
talk.
to drop your email, if you like prefer, that'd be great. Thank you. And I just dropped a couple of links. So if you wanna watch other DeepSense sessions, you can like click on that link. And if you wanna follow us on social media, that's a great way for you to like keep up with our upcoming discovery sessions. Thanks again, everyone. Enjoy the rest of your day, and I hope to see you all again at the next discovery session.
Thank
Bye.
you.